So, you have two people. They have Bob and Alice, okay? And, oh, there's some left. There's Bob and Alice, and Alice knows a secret password. So, and the password is binary. So some mystery sequence of codes, and it's of length n. And Bob needs to guess the password to authenticate himself. Bob actually doesn't know the password. Alice has some secret binary code of length n, and Bob needs to guess the password. So we want to write an algorithm to crack this password. What would one algorithm be?
Try every combination.
Brute force it. Okay, try every combination. Is there anything that I can do that's so brute? How long would that take?
16 in this case.
Yeah, in this case it's 4, but if it's n. Okay, so big O of 2 to the n. So Bob has to try sending big O of 2 to the n possibilities. And Alice will verify if one of them is correct. Can we do better than 2 to the n? Is there a way to reduce this problem into smaller versions of itself? Like, if I guess, let's say, I try to do some dynamic programming and I try to take suffixes of the password, will it help me in any way?
No.
No, why? You're right. You're right, but why not? Because what this bit is doesn't depend on what any of these other bits are. There's no dependence, there's no way of reducing problems smaller to itself. So what I claim is it's highly unlikely that this problem has a polynomial time solution. So highly unlikely. So intuitively, the way you can think about problems that are NP-hard is that it's very, very, very unlikely that you can find a polynomial time algorithm to solve the problem. Informally, I like to say it's exponential time, but that's wrong, so don't say that. But if you see a decision problem, and you're like, wow, I really cannot think of a polynomial time solution to this problem, it may be NP-hard. So a quick overview of the complexity classes. So first of all, this class of problems focuses only on decision problems where the answer is Boolean. The answer is true or false. The answer is yes or no. Is this the right password? Is it not the right password? For example, I could give you a list and I could ask you the question, is this list sorted? Can you solve that in polynomial time? How? You iterate through the list and compare every 2 consecutive elements. So these complexity classes describe problems that are decision problems. For example, does the graph have a Hamiltonian path? Yes or no? Is k the minimum cost tour? Etc., etc. So we want to understand what each one of these things mean. So formally, we can say a problem is NP if a deterministic Turing machine can solve the problem in polynomial time. Intuitively, the way we think about it is, I give you the problem. Can you solve the problem and give me a yes or no answer in polynomial time? Can you write an algorithm to solve the problem in polynomial time? A problem is an NP if one of 2 ways of looking at this. Can a non-deterministic Turing machine solve the problem in polynomial time? So for example, I'm sure you guys have been introduced to SAT already in lecture. So I give you an arbitrary formula, some 3-set formula, which A or B or C and E or A or B or C not. And you want to know, is phi satisfiable? Does there exist an assignment of 0s and 1s to phi such that this formula is true? We claim that this problem is NP because a non-deterministic Turing machine can solve the problem in polynomial time. How? It guesses the right assignment and it verifies it. So you could say you have some non-deterministic Turing machine that guesses the assignment, and 2, verifies the assignment. So I want to hone in on the second part. If guessing the assignment, it does non-deterministically. It just doesn't. How do we verify the assignment? If I give you an assignment of true and false to literals in the string, how do you tell if that is a satisfying assignment? Yeah?
Plug it in.
Plug it in. So let's say I say A is 1, B is 0, C is 1. Let's try this, okay? 1 or anything is 1, so this is good. And B was 0, so A complement is 0, so that's false. B is 0, so that's false. C complement is 0, so this is 1 and 0, and this evaluates to false. If I try setting all of these to 1, what happens? A is true, so this is true. B is true here, so this is true. If I take the AND of both of these, I get true. So one way of viewing the complexity class NP is forgetting the whole non-deterministic Turing machine thing, because the guessing part is trivial. The verification part is what we want to hone in on. So if I give you a problem, which is SAT, I give you a problem instance, and I give you a certificate consisting of proof that the answer is yes, can you examine that certificate in polynomial time and confirm if the answer is yes? Think about it like this. I claim that I'm Google Cloud certified. I'm not. I don't know anything about Google Cloud. Okay? I'm applying to a job, and the person on the other end wants to verify that I am in fact Google Cloud certified. So what proof do I need to hand over to this guy? Well, I need to hand over to him the official certificate from Google. He inspects it in polynomial time, and he's like, yep, this guy's good. And he gives me the job. I wish. So another way of viewing the complexity classes. So P, I said, can you write a polynomial time algorithm to solve the problem? NP, given a problem instance, which is a specific graph, a specific formula phi, a specific configuration, and proof, by proof I mean a certificate, can you verify in polynomial time that the answer to the question is in fact yes? So solving a problem versus verifying the correctness of somebody else's solution to the problem. Another example, okay? So suppose I want to know, does the graph have a Hamiltonian path? The problem instance is the graph G, and the certificate is the sequence of vertices that form the Hamiltonian path. How do I verify, if I give you a graph G, and I give you a path consisting of a sequence of vertices, how do you verify if that path is in fact a Hamiltonian path?
Just traverse it.
I start tracing through the vertices in the certificate that I've given you, and make sure that every single edge exists. If that's the case, then I have a Hamiltonian path. So NP, the complexity class NP, formally you can think of it, is given a certificate and a problem instance, can a certifier algorithm take in both that certificate or proof that the answer is correct and the problem instance itself and tell you if the problem is a yes instance in polynomial time? A problem is NP hard. So questions about 1 and 2 so far before I move on.
So
Yeah.
a certificate is just saying that, oh, this solution is true? Is that
A certificate is proof that the answer is yes.
answer is yes?
So for the Hamiltonian path problem, if I give you a graph, to prove to you that this graph has a Hamiltonian cycle, I can give you a sequence of vertices. For the SAT problem, to prove to you that this assignment is satisfiable, I give you phi, which is the problem instance itself, and I give you an assignment of Boolean values to literals, and you, in polynomial time, verify that this assignment actually works and that the answer is a yes instance.
So it's like a proposed solution.
Yes. So
Possible.
it's a possible solution,
But not
but what it means is if the possible solution that I give you is a valid solution, you can tell me that is the case in polynomial time in terms of the size of the input and the size of the certificate. So let me put it this way. If I say, does a graph G have a Hamiltonian cycle? And I give you as a certificate all possible subsets of vertices. That subset of vertices is now exponentially large in the size of the graph. So this implicitly limits the certificate size to sort of be polynomial in the size of the input. Or you could argue that I'm only going to read the first order n bits of the certificate. So does everyone understand the class NP? Okay. NP hard. How should I do this? I'm going through this in detail because I think students find this pretty conceptually challenging usually. So,
wait.
Yeah.
So P is also a subset of NP, right?
Right. So if you can tell me if a list is, so let's consider a classic problem in P. Is this list sorted? How do you tell me if the list is sorted? You compare every consecutive 2 elements, and if it is sorted, you return true. Now I want to know, the question is a given list L sorted? I want to prove that it's an NP. Do I need to give you any additional proof to verify it?
No, we're going to run the same algorithm.
The proof set can be empty, and you can just run the same algorithm that you used to solve the problem to verify it. So one way of thinking about it is, if you can get the answer to a problem in polynomial time, then you can verify that problem in polynomial time. How? You solve the problem and compare the output to whatever someone else has given you. So that's the class P and NP. Now I'm going to talk about problems that are NP hard. So there's this famous theorem by Cook-Levin that proves that the 3-sat problem is NP hard. And 3-sat, remember, is you have literals of the form A or B or C. Dot, dot, dot. So you have clauses. This one thing is called a clause. You have clauses that OR 3 variables, and you have ands in between the clauses. So this famous problem was proven to be hard by Cook-Levin, I think. I don't remember. So the claim is, how do I want to show that a problem Y is NP hard? So I know that X is NP hard. So I have 2 problems, X and Y. I want to show that Y is NP hard, and I know that X is NP hard already. The argument that I want to construct is solving Y is at least as hard as solving problem X. So in order to solve problem Y, it will take at least as much time as it takes to solve problem X. So this idea of reductions is not new. We've seen it in language transformation when we converted one language into another. We've seen it in graph algorithms where we've modified the input graph and passed it into an oracle for BFS or DFS. Remember all the way back to lab 0 that languages are problems. Yes, instances of the language belong in the set, and no instances do not. So if I want to prove Y is NP hard, I want to prove that solving Y is at least as hard as solving X. So should I reduce from X to Y or Y to X? So option 1 is Y to X, and option 2 is X to Y. Raise your hand if you think it's 1. Okay, and raise your hand if you think it's 2. Okay. Why 1? For people who said 1, someone tell me why 1.
So if you can reduce Y to X, this means that you can Y with some polynomial time reduction, you can get to X. So that means that Y is at least as hard as X, because it would be hard. If it's harder to solve, you can reduce it.
Okay. So you're saying if I can if this is my problem Y, this is going to be an instance of problem Y. By an instance of a problem, I mean phi g, a graph, and this is an instance of problem X. Your claim is that if there's a polynomial time reduction from y to x, that means that y can be solved efficiently.
Y can be solved at the same time as x.
Okay, not in the same time.
Well, in a similar amount of time, I suppose.
Okay, let me say this. What if...
At least as much time to solve as x, I guess.
Sure. But not necessarily. And here's why. What if y was a really, really easy problem and x was a really, really hard problem? Let's say y is a problem that can be solved in constant time. So think of a really, push the limits of the definition here. Let's say y is a problem that answers, is this bit 0? Okay, you can literally just look at the bit and tell me. Constant time problem. Let's say this problem x is, does the graph have a Hamiltonian path? This is like exponential, well, supposedly exponential, NP-hard problem, right? Knowing that this problem is exponential in time doesn't affect my ability to solve problem y at all. How do I solve it? Well, the reduction is I don't call the function, and then just return, what is it? Iy equals 1, right? So we don't want to reduce from y to x. This direction is wrong because if y can be solved simply, x doesn't tell us anything about the complexity of y. So this direction is not right. Let's try x to y. Wait, questions about why this is wrong? Yes?
Which is basically like, if you reduce, like, or you just like, if you reduce an easy problem to a hard, that doesn't necessarily mean that the original problem is
right.
hard.
If you reduce an easy problem to a hard problem, that doesn't tell you anything about the easiness of the easy problem. Because if the original problem is really that easy, you can just solve it. And then you don't even need to use the oracle for the hard problem. So let's try the other direction now. We are now reducing from x to y. This is an instance of problem y. And then remember, x is our known hard problem. This is our reduction. Our reduction converts an instance of problem x into problem y. Yeah?
An instance is just like one singular instance that has like the decision yes or no, right?
An instance is an encoding of the problem itself. So in that case, right, the formula phi would be an instance of 3-set.
Like a particular example.
Yeah, a particular example. Your goal when you make a reduction is to convert arbitrary instances of y to specific instances of x. Sorry, arbitrary instances of x to a specific instance of y. So, anyways, okay, this problem x I know is really, really hard. I'm trying to prove that problem y is really hard. So, the claim is that x is NP-hard. This is known. Okay? We want to prove y is NP-hard. This is what we want to prove. So, let's say, so if y is NP-hard, what does that mean in terms of its ability to be solved in polynomial time? It's highly unlikely, right? Yeah, so if y is NP-hard, it's highly unlikely that there's a polynomial time solution to y. So if y is NP-hard, highly unlikely to have polytime solution. So if y is NP-hard, y is highly unlikely to have a polynomial time solution. So what does that mean? If this reduction runs in polynomial time, so let's say, suppose, for contradiction, y runs in polynomial time. Okay? Suppose y runs in polynomial time for contradiction, okay? That means there's a polynomial time reduction from here to here. So there's a polynomial time reduction, poly time reduction, from x to y. Okay? Does anyone see an issue here? So I said x is a known NP-hard problem. If we could solve y in polynomial time, and x could be converted to y in polynomial time, that would mean that x could have been solved in polynomial time. Right? So once again, the claim is that I'm trying to prove that y is NP-hard. I'm trying to prove that this is hard. Suppose this was actually solvable in polynomial time. Then I could convert x to this problem in polynomial time, solve this problem in polynomial time, which implies that I solved x in polynomial time, which is a contradiction because x is NP-hard. Therefore, this direction of reduction is the correct reduction to prove NP-hardness. Questions about this? Yeah?
So you're saying that every time we want to prove this, we want to prove by contradiction?
No. I am trying to prove why reducing in this direction is correct. If I want to prove that a new problem y is NP-hard, I reduce from a known NP-hard problem x to the problem y, instead of the other way around. Yeah?
So isn't it possible to have a reduction that is not poly time?
Yes. So my claim is, if there's a polynomial time reduction from x to y, that the reduction direction, not only do you reduce x to y, but it's also a polynomial time reduction from x to y.
So do we consider non-polynomial time reductions in this class?
No.
Okay, that is fine.
I mean,
because then my point was that if y is in polynomial time, but going from x to y is
no. So this is all predicated on the reduction being done in polynomial time, right?
Sure.
Okay, so back to the complexity class definition, and I'm spending time on this instead of doing lab problems because it's very important. So if a problem is both NP and NP-hard, then we say it's NP-complete. So to reiterate, a problem is in P if you can solve all. Okay, step 0, all of these problems are about decision problems where the answer is yes or no. If I can solve the problem and tell you if the answer to the question is yes or no in polynomial time, then the problem is in P. If I can take in an instance of the problem and some proof, which is a certificate, iterate through the certificate and verify in polynomial time that the answer is yes, then the problem is an NP. If I can reduce from a known NP-hard problem x to this new problem y, then y is NP-hard. And if the problem is both in NP and NP-hard, then the problem is NP-complete. Good? That was a lot. So I'm going to go through an example of one of these reductions.
Wait, what was NP-hard again?
NP-hard was this stuff. So if I can reduce from a known problem, that is a known problem x is NP-hard. I'm trying to prove y is NP-hard. If I can reduce from a known NP-hard problem to the current problem at hand in polynomial time, then the current problem is NP-hard.
Wait, how does, like, NP-hard contains, like, problems, some NP problems, right? But
Correct, but not all of them. Yeah.
And then NP-complete is the intersection of
NP and NP-hard.
And all, like, undecidable.
Well, don't worry about undecidability. The NP-complete, for now, we'll think about as the intersection of NP and NP-hard. For now. But so one student gave up. Okay. Hamiltonian cycle G is a cycle that goes through every vertex of G exactly once, Deciding whether an arbitrary graph contains a Hamiltonian cycle is NP-hard. So this is our known problem that's NP-hard. Hamiltonian cycle is NP-hard. A Tonian cycle in a graph, G, is a cycle that goes through at least half of the vertices in G. Prove that deciding whether a graph contains a Tonian cycle is NP-hard. So we have Hamiltonian cycle, and then we have the problem Tonian cycle. We want to prove that Tonian cycle is NP-hard. And then how did I say we prove something is NP-hard? We use a reference problem. So the reference problem that we're going to use is Hamiltonian cycle. And we prove it by reduction. So which way do I reduce? Do I reduce from Hamiltonian cycle to Tonian cycle? So option 1 is to Hamiltonian cycle, or option 2 is Hamiltonian cycle to Tonian cycle. Which one of these is correct? Option 2. Yes, exactly, right? And why is this the case? That's the proof I went through there. So we want to draw the diagram that we always do. Hamiltonian cycle. What is the input into the Hamiltonian cycle problem, and what is the output? Right, so the input, you want to make sure that you have these clear in your head. So the input is a graph G, and then the output, I can't spell, is true or false if G has / doesn't have Hamiltonian cycle. Okay, and then what is the input and output to the Tonian cycle problem?
Would there not be a certificate as an input as well? Or?
I'm just talking about the problem itself. I'm not talking about the verifier.
Okay.
Yeah. What is the input to the Tonian cycle problem?
So a graph.
Okay, a graph G. And then what is the output?
Also true, false, or if it has or doesn't have TC.
True if what?
True if it has a Tonian cycle.
Right, which is?
Sorry. It has half the, it goes through at least half the vertices.
Right, a cycle that goes through at least half the vertices.
Is it only once, or is it at least half the vertices? Is it half the vertices exactly once, or is it half the vertices a number of times?
What do you mean by a number of times?
Any number of times, sorry. Because I know for Hamiltonian cycle, it goes through all the vertices exactly once.
Yeah, exactly once.
So the TC for the Tonian cycle, is it
exactly
once?
Once, yeah. Okay. True if there exists a path that goes through all vertices, or half of the vertices in G, exactly once. False otherwise. So all I've done here so far is just list the problems. A Hamiltonian cycle, a graph G has a Hamiltonian cycle if it visits all of the vertices in the graph. A graph has a Tonian cycle if you have a cycle that visits exactly at least half of the vertices in the graph. So based on this argument that we said here, we want to use the Tonian cycle problem as an oracle. So we want to reduce the Hamiltonian cycle problem in polynomial time to the Tonian cycle problem. So we have an instance of the Hamiltonian cycle problem, which is a graph. And we have an instance of, we want to convert it into an instance of the Tonian cycle problem, which is, we're going to call G prime, such that if G has a Hamiltonian cycle, G prime has a Tonian cycle, and if G does not have a Hamiltonian cycle, G prime does not have a Tonian cycle. Yeah?
I thought we were doing it the other way around, TC to HC.
No. So it should be, we want to, so we're trying to prove that Tonian cycle is NP-hard. We know for a fact that Hamiltonian cycle is NP-hard. So the claim is, if we go back over here, we know as a fact that the Hamiltonian cycle is NP-hard, correct? Suppose that Tonian cycle was solvable in polynomial time for contradiction. So suppose we could solve Tonian cycle in polynomial time. Good so far? If we could reduce Hamiltonian cycle to Tonian cycle in polynomial time, and we could solve Tonian cycle in polynomial time, then there would be a contradiction because then that would mean that we could solve Hamiltonian cycle in polynomial time. So that's why we're reducing from Hamiltonian cycle to Tonian cycle. Is that clear? Yeah. Okay. So let's draw some graphs that have Hamiltonian cycles. So does this graph have a Hamiltonian cycle, yes or no? Yeah. Give it to me. A, B, E, C, D, technically back to A. Yeah. Okay. So what we want to do is we have an oracle for Tonian cycle. Somebody else built it. We don't care how it works. This magical black box tells us if G prime has a Tonian cycle. How do we convert a graph that has a Hamiltonian cycle, i.e. a cycle that visits every vertex exactly once, into a graph that has a cycle where exactly half of the vertices are, at least half of the vertices are visited? So I have a graph that has a path that has a Hamiltonian cycle in it. I have a black box on the desk that tells me, does this graph G prime have a cycle that visits at least half of the vertices? I want to modify my input graph G and pass it into the oracle. How should I make the modification? Yeah.
So the algorithm that you have for Tonian cycle already tells you.
Yeah, so I'm not trying to solve the Tonian cycle problem. I have an oracle for the Tonian cycle problem. I'm trying to solve the Hamiltonian cycle problem using the Tonian cycle problem as a black box, which means I want to convert an instance of the Hamiltonian cycle problem into an instance of the Tonian cycle problem. In the same way, we do some graph alterations and then we run BFS. Yeah?
You just like remove half of the vertices in the graph and pass it through the black box.
Okay. So idea one. Remove half of the vertices. In G and pass it into Tonian cycle. To Tonian cycle. So I'll ask you this. This is my graph G, right? What half vertices should I remove in G before I pass into Tonian cycle here?
Remove A and B.
I can remove what?
A and B.
Wait, do you even need to? Because it says at least half.
Yeah.
If it goes through all of them already, that covers at least half by definition.
Yeah, but it's okay. So
That's the yes.
yeah, so that's for the
Yes,
essence.
but
So
then
your
no,
idea,
but
yeah.
no.
So his idea is like, wait, I have an oracle on the desk that tells me if my graph that I pass into it has a cycle that goes through at least half of the vertices.
If it goes through all the
My original graph, if it goes through all of the vertices, goes through at least half of them,
works for yes.
right?
Not for no.
But not for no,
Mhm.
because if I have a graph that goes through n over 2 plus 1 vertices and I pass it into the oracle, it's not going to work. So his idea was, okay, let's remove half of the vertices. So I asked, which half vertices do you want to remove here? So actually, okay, let's put it here. I have an odd number of vertices. So do I want to remove 2 or 3?
2.
Okay, I will say, what are we trying to do again? We're trying to determine if the graph G has a Hamiltonian cycle.
We are. Tonian cycle, yes.
No. We want to know if this graph has a Hamiltonian cycle.
Okay.
We want to use the oracle Tonian cycle to solve the problem.
Oh, I see.
We want to convert if a graph has a Hamiltonian cycle, we want to convert G into G prime such that G prime has a Tonian cycle. If G does not have a Hamiltonian cycle, we want to convert G into G prime such that G prime does not have a Tonian cycle.
Okay.
So we're not trying to solve the Tonian cycle problem.
We're solving the existing problem.
Yes, we're solving the Hamiltonian cycle problem using the Tonian cycle problem as an oracle. So let's think. I have a black box on the desk that tells me if my graph has a cycle that goes through at least half of the vertices. I'm trying to solve the problem of whether my current graph, G, has a cycle that goes through all of the vertices. Yeah?
What if you like pull all the vertices and then don't connect those to anything? Then like you'll have like half of them, like if at least half of them can be connected, and that's the Hamiltonian path of your original thing.
Exactly. So, what his idea was is, I have my graph G. So you were on the right track, but in the wrong direction. Instead of having the number of vertices, we wanted to double them. So in this case, G has a Hamiltonian cycle. So G has a Hamiltonian cycle. And here it is. We want our reduction to build G prime such that G prime has a Tonian cycle. And how we want to do that is, I make a copy of the original input graph. And then, as he said, what if I just double the number of vertices and don't connect them to anything else? So 1, 2, 3, 4, 5. It doesn't really matter what I call them. So this whole thing over here is my new graph, G prime. Does G prime have a cycle that goes through at least half of the vertices? Does this graph have a cycle that goes through at least half of the vertices?
Yes.
1, 2, 3, 4, 5, and I have 10 vertices in total. So, in this case, if G has a Hamiltonian cycle, if G has a cycle that goes through all of the vertices, G prime has a cycle that goes through at least half of the vertices. Let's consider a case where G prime doesn't have a cycle, doesn't have a Hamiltonian cycle. Oh, sorry, G, thank you. A, B, C, D. Here, my graph G does not have a Hamiltonian cycle because I never visit E. If I apply the same transformation to get G prime, well, first I make a copy of the original input graph, which was A, B, C, D, E. And then I add a bunch of other vertices in. How many? 5 more. 1, 2, 3, 4, 5. Does this graph G prime have a Tonian cycle? Does this graph G prime have a cycle that goes through at least half of the vertices? I have 4 out of 10, right?
Yeah.
So, our reduction is going back up here. If we have to describe the reduction that we're doing, step 1, we make a copy of G. Let's be even clearer. So our reduction it takes as input G and it outputs G prime. So it takes as input our original graph, it makes an output G prime, and it does this by making a copy of G, and then adding extra vertices.
With no connecting.
With no edges. Yep. So reduce is a function that accepts G. That's it. So questions about the reduction? Yeah.
I guess not about the reduction, kind of in general.
Mhm.
So we say Hamiltonian cycle here reduces to Tonian cycle.
Yes.
But the way we write it on top is in reverse. We write TC, then the little thing HC.
Say that one more time. So your question is?
So if we say that Hamiltonian cycle reduces to Tonian cycle,
Yes.
the way we write that is TC and then the little...
No. We write it like this. If Hamiltonian cycle reduces to Tonian cycle, the claim that is that solving Tonian cycle is at least as hard as solving the Hamiltonian cycle problem. Here, think about it like this. So, in order to solve the Tonian cycle, in order to solve the Hamiltonian cycle problem, okay, think about very simply, x reduces to y means that we're using y as a black box.
I guess, wait, when you had it number 2 and you had like it purple, was that highlighting you saying it was correct? Or was
Yeah, that was highlighting it. Oh, did that look like, sorry, did it look like that was crossing it out?
Yeah.
Oh, I'm so sorry, yeah.
It's okay.
Yeah. Okay.
Okay.
Okay, questions about the correctness of the reduction? Yeah.
So when you make a reduction like this on an exam, do you
You have to justify that it's correct, yeah.
you need to rigorously prove both the directions?
Yeah, so, but before we get to the proof, questions about the idea. You're right that we need to do that. So what you need to prove that the reduction holds true in both cases. So in the forward direction and the reverse direction. So if G has a Hamiltonian cycle, so this is the forward direction. If G has a Hamiltonian cycle, then G prime has a Tonian cycle. Why? If G has a Hamiltonian cycle, G has a cycle that visits every vertex in the graph exactly once. If I add V extra vertices to G and construct G prime, G prime now has a path that visits exactly half of the vertices in G. Since G prime has a cycle that visits half of the vertices in G, G prime has a Tonian cycle. So if G has a Hamiltonian cycle, G prime has a Tonian cycle. So that's the forward direction. In the reverse direction, you would argue that if G prime has a Tonian cycle, then G has a Hamiltonian cycle. So why is that the case? If G prime has a Tonian cycle, G prime has a cycle that goes through exactly half of the vertices in G. The reduction that we constructed does not add any edges to G in and of itself. The reduction that we constructed only adds vertices, which means that any edge that exists in G prime was originally an edge in G. So if I remove the vertices that do not have any edges connected to them, then I should restore my, yeah, what's up?
Wait, I thought you didn't, I thought the proving was just you just do the yes instance, show that that's a yes instance, no instance is no.
Yeah, so this is the same thing. So his question is, let me finish the argument and then we'll get there. So if G prime has a Tonian cycle, then I claim that G has a Hamiltonian cycle. Why? If G prime has any edges, if G prime has a Tonian cycle, it has a cycle that goes through exactly half of the nodes in G prime. The rest of the nodes, the reduction doesn't add any edges, so discarding half of the vertices means that those half of the vertices had to have come from the reduction, which means that the remaining graph G had a Hamiltonian cycle in it. So that's the forward and reverse directions. But yeah.
Well, do you need to prove forward and reverse that way, or can it be all yeses in G return yeses in G prime?
So either is acceptable.
Okay.
So the question is, do I need to, so there's two ways of doing this. I need to prove that yes instances of G map to yes instances of G prime, and yes instances of G prime map to yes instances of G, or I can prove that yes instances of G map to yes instances of G prime, and no instances of G map to no instances of G prime. Why is this the same? So essentially what I'm trying to prove with the first method I suggested is that P implies Q. Right? If P is yes, then Q is yes. So this is statement 1. Statement 2 is that Q implies P. Right? But this is logically equivalent to saying that not P implies not Q. Right? So he said no instances of P map to no instances of Q, which is the same thing as justifying that yes instances of Q map to yes instances of P. So either one is acceptable. Okay, so that was the proof that the problem is NP-hard. Why? We found a polynomial time reduction from a known NP-hard problem, which is the Hamiltonian cycle problem, to the Tonian cycle problem y, which we're trying to prove is NP-hard, is the Tonian cycle problem in NP? Yeah.
Yeah, because if like with your Tonian cycle, you can verify that
Right. So
it covers half, at least half, and then it is a cycle.
correct. So what is the? So we call the algorithm that verifies it a certifier algorithm. So the problem instance is the graph. What is the certificate? The proof. Yeah. What is the proof?
Oh.
You just said it. Yeah.
I mean, yeah, you check whether the cycle has half the vertices, and then you check that it's a cycle.
Right. So the proof is the sequence of vertices that form half the cycle.
Yeah.
Then in polynomial time, you iterate through that certificate and check if every edge exists. So the problem is an NP. It's NP hard. So what does that mean? The Tonian cycle problem is NP complete.
Wait, doesn't the Tonian cycle return like a Boolean?
Yeah.
Or is that?
Exactly.
So if it gives you true, you have to go and check the graph itself. Okay, sure.
Yeah. Wait, sorry, I didn't understand the question.
So because you're given a like possible solution. And
You're
certifying
given.
it, right?
Are you talking about proving that a problem is NP?
Yes. So you're given a possible solution. If in this case the problem returns true, that means your possible solution is true. So then how do you prove
No.
that
So
it's-
a problem is in NP if when you give the correct certificate to the problem, you can, if you give it a problem instance and the correct
The
proof,
certificate
it
is not
verifies.
exact- So the certificate is not what it outputs.
The certificate is not what the algorithm outputs.
Okay. All right. Okay.
The certificate is proof that the answer to this question is yes. So
Oh, I see. Okay.
the idea here is if a non-deterministic Turing machine, let's say, guesses the vertices in the cycle, how do you actually verify that that's correct? You have to check if that sequence of vertices actually forms a Tonian cycle or not. So that's why the two views are equivalent. Yeah.
So the certificate is a suggested solution, right? It's
Yes.
not like an actual proof of that.
Right. The certifier algorithm accepts as input a certificate and a problem instance, iterates through that certificate in polynomial time, and verifies if you give it the right certificate, it will return yes.
So the certifier is the actual decision problem.
So for
The certifier problem is verifying that the answer to the decision problem is
correct,
yes.
yes.
So the input, say for now, for our input graph and our like certifier, is that going to is that feeding into our Hamiltonian?
No, completely disconnected concepts.
This
Completely unrelated. The reduction from Hamiltonian cycle to Tonian cycle only deals with the graphs themselves.
Okay.
That proves that the problem is NP hard because you're saying that solving Tonian cycle is at least as hard as solving the Hamiltonian cycle problem.
Yeah.
That just shows hardness. But to prove it's in NP, that's where the certificate certifier component comes in.
Like for just doing NP hard, the reduction would be enough.
Right. So for just doing NP hard, the reduction is enough.
But to show
To
that
just
it
show
is an
NP completeness, you need to show NP hardness and being an NP.
NP, and so then you'd say an input instance for the Tonian cycle and a certifier.
Yes.
And then can we check that not with an NTM
Yeah.
polynomial?
Correct. So the reason I did this instead of going through all of the lab problems is this lab only focuses on reductions, which I think is not a good holistic view of the overall set of complexity classes that you'll be tested on. So, yeah. Any other questions? Okay.